It is literally everywhere. The sidewalks you walk on, the bridges you cross, the massive skyscrapers that make up our cities, you guessed it, they're all made of concrete. But have you ever really stopped and thought about what gives this, humble material its incredible world-building strength? Well, the secret isn't just about mixing sand and stone. It's hidden deep inside its most important ingredient, cement.
Okay, so let's really get into this. We see concrete all day, every day, but what's the secret sauce? What is really giving this simple gray block its incredible strength? Well, the answer isn't something you can just see with your own eyes. To find it, we're going to have to go microscopic.
You see, the key to concrete's power is all tucked away inside that fine gray powder we call cement. So right now, we're about to uncover its secret ingredients. And I'm not talking about the obvious stuff here. I'm talking about a whole hidden world of microscopic crystals that controls pretty much everything.
Yeah, that cement powder, way before you even think about adding water, is way more complex than it looks. It's a highly engineered mixture of what scientists call crystalline phases. Just think of them as different types of tiny, perfectly formed little crystals. And the exact amount of each one of these phases, like alite, for example, which gives concrete its early strength, or belite, which helps it get stronger over time, that's what determines everything about the final product. How strong it is, how durable it is, and how long it's going to last.
So if the whole recipe is just about counting these microscopic crystals, how in the world do you do it? I mean, it's not like you can just pick them out one by one with a tiny pair of tweezers. No, you need a way to identify each one to get what we can basically call a crystal fingerprint. And that is where this amazing piece of technology comes in, X-ray diffraction, or XRD for short. Now, to put it simply, scientists take a sample of cement powder and they just shine a beam of X-rays at it. The way those X-rays bounce off, or diffract off the crystals, that tells them exactly what's inside. It's kind of like a high-tech census for microscopic stuff. So how does this actually work? Well, take a look. On the left, you can see that every single type of crystal has its own unique, perfectly ordered arrangement of atoms. So when X-rays hit that specific structure, they bounce off in a very specific way, creating this unique pattern of peaks you see over on the right. This pattern is a perfect, undeniable signature, a fingerprint, for each and every type of crystal.
Now that sounds pretty straightforward, right? You just look for the fingerprints and you count them up. But here's the catch. In a real-world cement sample, you're not dealing with one nice, clean fingerprint. No, you're dealing with a total jumble of clues.
And this right here shows you the problem perfectly. This is a real XRD scan from a cement sample. And you can see it is not one clear fingerprint. It's dozens of them, all mashed together and overlapping. The peaks from a really important crystal like alite are sitting right on top of the peaks from ferrite and gypsum. It's a mess. So how on earth do you even begin to read this?
The researchers who work with this stuff every day put it perfectly. They say the peaks, which they call reflection lines, have considerable overlap. And for decades, this was a massive challenge. You couldn't just measure a single peak to figure out how much of something you had, because that one peak might be contaminated with signals from 2, maybe even 3 other crystals.
So, if this messy XRD scan is like a crime scene with dozens of fingerprints all smudged together, what do? Well, you need a master detective to sort through all the evidence. And in the world of materials science, that detective has a name, the Rietveld method.
The Rietveld method is a total game changer, and it's all done with computers. It doesn't even try to look at one peak at a time. No, its genius is that it analyzes the entire jumbled pattern all at once. It already knows the perfect fingerprint for every possible crystal, and it uses some pretty powerful math to figure out the exact combination of those pure fingerprints that adds up to create the messy pattern from our real sample.
And here it is. This is the Rietveld detective at work. Look at that top line. That's the same messy, overlapping pattern we saw before. But now, look below it. The software has mathematically taken that mess completely apart, pulling out every single individual fingerprint. You can clearly see the separate signals from alite, from belite, from ferrite, and all the other little ingredients. The puzzle is officially solved. And with the puzzle solved, the detective gives us its final report. This table, right here, this is the result. We now know with incredible precision that this particular cement sample is made of 69.7% alite, 10.8% ferrite, and so on down the list. What this means is we've gone from a super confusing jumble of data to an exact quantitative recipe. The hidden code of the cement has finally been cracked.
But, as any good detective knows, your analysis is only as good as the evidence you collect at the crime scene. And in the world of XRD, that means your sample preparation has to be absolutely perfect. And listen, this isn't just some minor technical detail. It is the foundation of the entire process. If that cement powder isn't prepared just right before it goes into the machine, you are not going to get clear fingerprints. You'll get a blurry, unreliable signal, and even the brilliant Rietveld detective won't be able to give you an accurate answer.
And this slide shows you exactly what a difference it makes. I mean, just look. On the left, that's the pattern from a sample that wasn't ground up finely enough. The peaks are all spiky and sharp and irregular. This data is basically noisy and untrustworthy. But look at the right. After that same sample was properly ground into a superfine powder, the pattern becomes clean, smooth. This is high-quality evidence.
So getting that high-quality evidence takes a few really crucial steps. First, the cement has to be ground into an ultra-fine powder, ideally with particles smaller than 10 micrometers, just to make sure you get a good average. Second, you have to mount that powder carefully so the crystals are all just randomly jumbled, not lined up in one direction. And finally, if you're actually studying cement as it's hardening with water, you have to instantly stop the chemical reaction to basically freeze a perfect snapshot in time.
Okay, so this is some seriously cool material science. But why does it really matter in the real world? Why go to all this trouble just to decode a bag of cement?
Well, because accuracy matters a lot. This chart right here compares the super precise Rietveld result for allalite, that's the main strength-giving crystal, remember, with an older estimation method. The old method was off by over 10%. That is a massive error when you're dealing with the performance and even the safety of a material we use to build our entire world. Getting it right isn't just better, it's absolutely essential. So when you get down to it, decoding cement with this level of accuracy, it changes everything. It means we can have strict quality control, making sure the buildings and bridges we rely on are actually safe. It means we can understand durability so much better and build infrastructure that lasts not just for decades, but for centuries. And looking ahead, it drives innovation, giving us the tools to design stronger and way more sustainable next-generation cements with a much smaller carbon footprint.
So, we started with a simple gray block and ended up deep inside its atomic structure. We found a total jumble of clues and used a powerful computational detective to finally crack its hidden code. And all of that leaves us with one last question to think about. Now that we can finally read this code, what incredible things can we build next?